In our first section, we will talk about structural metals and their properties. Of primary concern in aerospace maintenance are such general properties of metals and their alloys as hardness, brittleness, malleability, ductility, elasticity, toughness, density, fusibility, conductivity, and last, contraction and expansion. Hardness refers to the ability of a metal to resist abrasion, penetration, cutting action, or permanent distortion. Hardness may be increased by cold working the metal, and in the case of steel and certain aluminum alloys, by heat treatment. Structural parts are often formed from metals in their soft state and are then heat treated to harden them so that the finished shape will be retained. Hardness and strength are closely associated properties of metals. Brittleness is the property of a metal which allows little bending or deformation without shattering. Cast iron, cast aluminum, and very hard steel are examples of brittle metals. A brittle metal is apt to break or crack without change or shape. Because structural metals are often subjected to shock loads, brittleness is not a very desirable property. Cast iron, cast aluminum, and very hard steel are examples of brittle metals. Malleable refers to metal which can be hammered, rolled, or pressed into various shapes without cracking, breaking, or leaving some other detrimental effect. This property is necessary in sheet metal that is worked into curved shapes such as cowlings, fairings, or wingtips. Copper is an example of a malleable metal. Ductility is the property of a metal which permits it to be permanently drawn, bent, or twisted into various shapes without breaking. This property is essential for metals used in making wire and tubing. Ductile metals are greatly preferred for aerospace use because of their ease of forming and resistance to failure under shock loads. Chrome molybdenum steel is also easily formed into desired shapes. Ductility is similar to malleability. Elasticity enables a metal to return to its original shape when the force which causes the change of shape is removed. This property is extremely valuable because it would be highly undesirable to have a part permanently distorted after an applied load was removed. Each metal has a point known as elastic limit beyond which it cannot be loaded without causing permanent distortion. In spacecraft construction, members and parts are so designed that the maximum loads to which they are subjected will not stress them beyond their elastic limits. This desirable property is present in spring steel. A material which possesses toughness will withstand tearing or shearing and may be stretched or otherwise deformed without breaking. Toughness is a desirable property in spacecraft metals. Density is the weight of a unit volume of a material. In the aerospace industry, the specified weight of a material per cubic inch is preferred, since this figure can be used in determining the weight of a part before actual manufacture. Density is an important consideration when choosing a material to be used in the design of a part in order to maintain the proper weight and balance of the spacecraft. Fusibility is the ability of a metal to become liquid by the application of heat. Metal are fused in welding. For example, steels fuse around 2600 degrees Fahrenheit and aluminum alloys at approximately 1100 degrees Fahrenheit. Conductivity is the property which enables a metal to carry heat or electricity. The heat conductivity of a metal is especially important in welding because it governs the amount of heat that will be required for proper fusion. Conductivity of a metal to a certain extent determines the type of jig to be used to control expansion and contraction. In spacecraft, electrical conductivity must be considered in conjunction with bonding to eliminate radio interference. Contraction and expansion are reactions produced in metals as a result of heating or cooling. Heat applied to a metal will cause it to expand or become larger. Cooling and heating affect the design of welding jigs, castings, and tolerances necessary for hot rolled material. Strength. The material must possess the strength required by the dimensions, weight, and use. There are 5 basic stresses which metals may be required to withstand. These are tension, compression, shear, bending, and torsion. Tension. The tensile strength of a material is its resistance to a force which tends to pull it apart. Tensile strength is measured in psi, pounds per square inch, and is calculated by dividing the load in pounds required to pull a material apart by its cross-sectional area in square inches. Compression. The compression strength of material is its resistance to a crushing force, which is the opposite of tensile strength. Compression strength is also measured in psi. Shear. When a piece of metal is cut, the material is subjected, as it comes in contact with the cutting edge, to a force known as shear. Shear is the tendency of the part of parallel members to slide in opposite directions. It is like placing a cord or thread between the blades of a pair of scissors. The shear strength is the shear force in psi at which a material fails. It is the load divided by the shear area. Bending. Bending can be described as the deflection or curving of a member due to forces acting upon it. The bending strength of material is the resistance it offers to deflecting forces. Torsion. This is a twisting force. Such action would occur in a member fixed at one end and twisted at the other. The torsional strength of material is its resistance to twisting. Weight. The relationship between the strength of a material and its weight per cubic inch, expressed as a ratio, is known as the strength-weight ratio. The ratio forms the basis for comparing the desirability of various materials for use in airframe construction and repair. Neither strength nor weight alone can be used in means of true comparisons. In some applications, the material with the lightest weight for a given thickness or gauge is best. Thickness or bulk is necessary to prevent buckling or damage caused by careless handling. Reliability. Due to the extreme environments encountered by a spacelift system, either awaiting launch at a coastal, salt air-rich spaceport, or during post-launch flight through the atmosphere into space, the materials used must be carefully chosen to combine the best mix of corrosion resistance and workability. The Plymouth Prowler is a good example of where the selection of materials was an important criterion in the design and manufacturing process. This retro-style production car, built between 1997 and 2002, was designed with nearly 930 pounds of aluminum used in its construction, chiefly in the chassis. Not only did it reduce the overall weight, but was less costly than steel. Aluminum also places less wear and tear on machine tools in the manufacturing process.